Now we will talk on the use of kernels with SVM. So we saw that with basis functions, we can do a mapping from D dimensions to K dimensions using this basis function. So that new space, we can call this Z. Z is the result of the application of phi. And then with that new space, we can just see that, in fact, we are dealing with a linear discriminant. So we are applying the linear discriminant, but instead of working on X, we are working on Z. The rest is the same. So from this, we can develop the formulation that way. So basically, it's re-expanding, getting back on the phi X here. We can develop this and formulate this into some kind of dual forms. We can simply state that the W in of our linear discriminant in the space spanned by Z, so the bigger space, is corresponding to the sum of alpha T RT ZT here, which is corresponding to the alpha T RT phi on XT. So we have this for all samples of our training set. So with this reformulation, we can fall back on this. So we can just simply state that h of x is corresponding to the sum of alpha t RT, the projection of x according to the basis function, so with the phi xt transpose times phi xt, phi x basically, plus w0. So this new formulation is kind of possible, and it's mapping directly from what we saw before with SVMs. The point is to replace, maybe just getting back here, to replace that whole thing with something else, which we call the kernel function. So that kernel function, which is defined that way, is possible. And in fact, it is a mathematical object that is kind of well known, well studied. And so with SVMs, we can use such kernel function directly in our formulation. So basically now, the h of x is defined as the sum over all samples of alpha t RT times the kernel function, which is looking at the relation between xt and x. So we have a data x here that we want to classify, and we will look at the relation of that x with all other xt that we have in our training set. So we are summing from t equal 1 to t equal n, and we are looking at the relation between x and xt. And we are multiplying this with the sign of xt and the alpha t. Of course, if we want to be efficient, if we want to make this faster in terms of computation, we may replace the loop of the sum over all samples by summing over all support vectors, because these are the vectors where the alpha is non-zero. So we just have to skip the cases where the alpha is equal to 0, which should be a majority of the samples in the training set. The nice thing is with that kernel function, it's really where we are doing a nice trick, is the fact that we are never computing, making computations directly in the space spanned by phi x. So the big space, when we are projecting from space in d dimensions to a space in k dimensions, that space in k dimensions, we can have a really big k. The k can be huge. But with the kernel trick, we are never doing computation in that big space. We are always making a computation by the kernel function, which is putting in relation all the samples. So we can avoid to compute anything in the high dimensionality space. So, and in fact, we can even deal with infinitely, a space of infinite dimensions or nearly infinite dimensions without working directly on it. Here are some commonly used kernels. We have the scalar product, which is basically the kernel we are falling back on the original formulation for linear discriminant. It's doing nothing but the x transpose y computation, so the product between x and y. But we have other kernels like the polynomial kernel of order k, which is basically computing this like x transpose y plus 1 power q. So this is a relatively common kernel that is doing a good job. We also have the same for Gaussian kernel, where we are applying basically the radial basis function, but on x and y. And if we simplify the equation, we get back on that thing. So basically exponential of minus the norm between x and y square divided by sigma square. So this is corresponding to the RBF, where we put a Gaussian function over all the support vectors. And we have also the sigmoid function, which is another one, which is the tan h apply on 2x transpose y plus 1. So these are common kernels that we can use. And then for the SVM kernel, we want to train, for example, on a data set here. We have our data set of n samples. How can we deal with that? We want to calculate the alpha by quadratic programming. So we are using the soft margin formulation with the dual formulation, in fact, where we want to maximize this equation. What is different from what we saw just before with the soft margins is that kernel function. We are using a kernel function that is comparing xt with xs. So we are like computing this thing over all samples of the training set using the kernel function. The rest is the same. I mean, all the formulation is the same. It's just that we are doing this with the kernel function. So we are kind of mapping this in a high dimensionality space. And the bias, W0, is computed as we explained before. We are computing the average over all support vectors. But what is changing now is that thing again. We are making use of the kernel function instead of dealing directly with the product of xt and xs. And for evaluating the data is the same. We are replacing that part. The rest remains the same. For example, if we develop the idea of using a polynomial kernel of order q, we have this equation in 2 dimensions with an order 2. So we can develop this directly that way. So we see that we have x transpose y plus 1 power of 2. So developing this with 2 variables, we get into that thing. Simplifying a little more, we can get into this corresponding basis function. So we can factorize, we can develop the factors of that equation into this thing. So basically we have the phi of x, which is made in fact of 6 dimensions. We have the dimensions of, this is constant, square root of 2x1, x2, x1 times x2, x1 square, x2 square. So this is corresponding basically to this product. So it's like this thing using that correspond to that thing, and that is equivalent directly to that. So the nice thing is that we see that this seemingly simple formulation get us with a mapping from 2 dimensions into 6 dimensions that are described by this thing. So it is possible to do that analytically for this specific setting, polynomial kernel, 2 dimensions, order 2. For the other cases, it's much more complex to make this development. It's not that easy. But we have a case that is illustrating this well here. For the Gaussian kernel, with a Gaussian kernel, we have a spread sigma here that is describing the size, I would say, how large is the influence of that kernel. And basically, we are computing the Euclidean distance between x and y squared, and using this in the exponential formulation. We can simply see a SVM with Gaussian kernel as equivalent to what we call a network of RBF functions trained in a particular way. So this is a kind of, I would say, it maps to some kind of advanced setting where we can explain what is doing that thing. So basically, it's like to use the SVM, but the SVM is kind of adjusting the W here of exponential functions, of Gaussian kernel, Gaussian functions that are placed on the different supervectors. So stated otherwise, we have RBS functions that are centered on the support vectors, and with we are learning somehow the influence of these support vectors in the decision, and that is making us a nice nonlinear classifier. We can even relate this to density estimation. With density estimation, we talk about kernel density estimation. These kernel in kernel density estimation are the same kind of kernel that we are using here. So the notion of kernel is really similar. And so the KDE, the kernel density estimation with Gaussian kernel, is a tool that has something similar with SVM. So it's basically like a SVM with an alpha equal to 1 for all samples. So we can see that the SVM, where we will get everything as a support vector in the training set with an alpha equal to 1, will result in some kind of density estimation in that space. But with SVM, we are not looking at estimating the density. We are looking at classifying with a model that has the maximal margin. So this is what we are aiming for. So some examples here of applying SVM. At first, we are starting with linear SVM. So this is SVM with the linear kernel, or basically with no kernel. We can see the kind of classification it is making here. These are the placement where I would say we are looking to get I would say a good setting. So on the right side, we can see this. We can see that all the circle data are data in the margin. So we have still a bunch of many data in the margin, but we have a relatively big margin, and the placement somehow makes sense. You know, it's probably the placement where we will get the best performance, but we know that we are still stuck with the linear model. So the model has to be aligned here, has to be really a separating hyperplane. We cannot do anything more fancy than that in terms of our model. So the model is limited by the formulation with a linear discriminant. If we are applying the same technique, but this time with a polynomial kernel, we are able to do some more elaborated model. We can see here that we have this model on which on the left is kind of more global. We see this more globally. So we have this frontier that has a bump in the middle, which makes sense if we look at the distribution of the red and yellow samples. We can see that the margin is also getting big at that position. That's because there is some ambiguity, and I think there are many samples that are considered in the margin here. But it makes sense according to our data set. I mean, this is a correct way, but we can see on the right that there are many support vectors here. So many samples are in the margin, and then several of them are misclassified. But that's probably, that seems to be the best we can do with that setting. This time with the same data, but using a Gaussian kernel, that's quite different. You know, the decision frontier has a very different shape. It seems to be much more fancy. You know, here we see that the decision frontier is kind of more, there's more variation. It's not a straight line, but it seems to be doing a good job in terms of really separating the two type of data. There are much less misclassified sample in that case. Still some, but not that much. What is interesting to see is that, you know, there is some kind of decision frontiers here. So like all the margin is defined really by this dashed line. So we can see that the data that are not in the margin are really the data in that zone. Everything else elsewhere for the yellow values are in the margin. And likewise for here, you know, all this region is correct. These are not support vectors, but everything else in that zone are considered as in the margin, whether they are correctly classified or not. So we can see on the right with some zoom in that region that they are still less data in the margin than before, but we can also see that the decision frontier are kind of more fancy than what we had with polynomial kernel. But we can change the behavior with the Gaussian kernel by using a large sigma. So with a large sigma, each Gaussian position on each support vectors has a bigger influence. So the sigma is large, influence is more important. So it gets into something much straight. You know, it's kind of much more simple model. It's not a linear model, but it looks like more a quadratic model that is fit here with what it implies. But it's still something that is doing the best given the sigma we are using, but possibly that sigma is too big for this data. And likewise, with a really small sigma, it tends to have many support vectors that are a really local influence. The influence is really small, such that we can get things like, I would say here, you see on the right, this is not that normal to get this kind of region with data in this kind of hole in the region without margin. And same thing here, you know, this is something that we saw in that region also. These are not necessarily good way to split the thing. So these are cases where the sigma is probably too small.